Hi, all of you. This is Dr. K. Nagareddy, Professor of ECE, NBKRST. Would like to talk about continuous time Fourier transform. These are the list of contents to be discussed. One is introduction, Fourier transform, properties of Fourier transform, convolution, PARSEVAL'S theorem. So coming to the introduction, why do we go for Fourier transform? Fourier transform is a process of converting a time domain signal into frequency domain signal. So why we are trying to convert the time domain signal into frequency domain signal means the analysis of any signal is very easy. That's why we are going for Fourier transform. Coming to the Fourier transform, we try to derive a simple equation for Fourier transform from the Fourier series equation. The Fourier series of any continuous time signal can be written as n equal to sigma n equal to minus infinity infinity Cn e power jn omega naught t dt, where Cn can be defined 1 over t integral minus t by 2 to plus t by 2 f of t e power jn omega naught t dt. So if I substitute the Cn over here, integral minus t by 2 to t by 2 f of t power jn omega naught t d tau into e power jn omega naught t. So if I do it, I can write omega naught equal to 2 pi by t and 1 by t equal to omega naught by 2 pi. So I can write 1 by t can be written as omega naught by 2 pi here. So 1 over 2 pi integral sigma n equal to minus infinity integral t naught t by 2 minus t by 2 to plus t by 2 f of tau e power minus jn omega naught tau d tau into omega naught e power jn omega naught t. So here let delta omega equal to omega naught. I am just assuming omega naught equal to delta omega, maybe 2 pi by capital T, and delta omega becomes d omega as t tends to infinity. So if I write t tends to infinity, 1 over 2 pi sigma n equal to minus infinity infinity minus t by 2 to plus t by 2 f t of tau e power jn omega naught tau d tau e power jn omega naught t delta omega. This can be written as the summation becomes integral 1 over 2 pi integral minus infinity infinity t tends to infinity minus infinity infinity f t of tau e power j omega tau. N omega naught may be represented as omega d tau e power j omega tau d tau. So this can be written as Fourier transform of the signal. And what could be the relation between Fourier series and Fourier transform? So Fourier series being defined like this, and Cn may be defined already like this, and Fourier integral equal to f of t equal to 1 over 2 pi integral minus infinity into f of j omega e power j omega t d omega. This is also called as inverse Fourier transform of the signal. And f of j omega equal to integral minus infinity into f of t power j omega t dt is the Fourier transform of the signal. So here I can have the first one is a period signal, and this is a non-period signal, and you can have a spectrum. This is called discrete spectra, and this is called continuous spectra. So Fourier series of any signal is a discrete spectra, and Fourier transform of any signal is a continuous spectra. So here we have two equations. One is a Fourier integral, another is a Fourier transform. So Fourier integral is called synthesis equation, and Fourier transform is called analysis equation. So Fourier transform and the Fourier integral also called as inverse Fourier transform, I can write. And we have a Dirichlet conditions like Fourier series. So what are the different Dirichlet conditions means the signal f of t should be integrable, and the signal should have a finite maxima and minima and finite number of discontinuities in any finite interval. So continuous spectra, we have once you find out the Fourier transform of the signal, the Fourier transform is always gives you a continuous spectra. So that is Fourier transform f of t equal to f of omega equal to integral minus infinity infinity f of t power j omega t dt is a continuous in nature. So this can be represented as a real and imaginary part of f of omega. Once you write real part and imaginary part, the x-axis may be represented as a real part of omega, y-axis you may represent as imaginary part of omega. You can calculate the magnitude as square root of fi square plus fr square may be represented as this. And the angle is tan inverse of real imaginary part per real part. So I can have phi of omega. So I can write this is modulus of omega into e power j theta omega. Theta omega can be written like this. So this is magnitude and this could be phase. And once you define what is a Fourier transform and what is the Fourier spectra, first of all, let us talk about elementary signal Fourier transform. So let us try to find the Fourier transform of a delta function equal to 1 at t equal to 0. So if I apply the formula x of omega equal to integral minus infinity into x of t power minus j omega t dt. So you replace x of t equal to delta t, and delta t will be exist only at t equal to 0. Then this becomes 1. The integral have no sanctity, and e power j omega t equal to 0, you have e power 0 equal to 1. So Fourier transform of delta equal to 1. So if delta equal to 1, Fourier transform of delta equal to 1 for all values of omega. So this is the time domain spectra, and this could be the Fourier transform spectra of it. So coming to the rectangular pulse, f of t equal to a for f of t equal to a for mod t is less than or equal to tau and equal to 0 elsewhere. This is the simple definition of the rectangular pulse. If you substitute this in the formula, I can have over the integral over minus tau by 2 to plus tau by 2 a e power minus j omega t dt, and integrate with respect to t and substitute the limits. I can get a tau into sine omega tau by 2 by omega tau by 2. This can be written as sampling a tau into sampling of. So sine omega tau by 2 by omega tau by 2 equal to sampling of tau by 2. So this is also called as a Fourier transform of a gating function equal to a tau into sampling of omega tau by 2. So here the Fourier spectra can be represented. So this is the time domain signal of the rectangular pulse, and this is the Fourier transform of the rectangular pulse is a sinc function or maybe a sampling function. Another example with omega with amplitude a equal to 1 and tau by 2 equal to 1, I can have the Fourier transform like this, and you will have a 2 sine omega by omega can be written as sine sampling of omega, and corresponding magnitude and phase spectra could be look like this. If I just vary the value of omega right from omega equal to 0 to 2 pi. So once you calculate the Fourier transform of a rectangular pulse, you can also calculate the Fourier transform of a constant by making tau tends to infinity. If I make tau tends to infinity, it becomes a rectangular pulse varies from minus infinity to infinity. So that is a constant. So if I use the formula which I have been given in the previous case, limit t tends to infinity f of getting gt of tau equal to a tau sampling of omega tau by 2. So you can take 2 multiply divide with 2 pi. You can have 2 pi into limit tau tends to infinity tau by 2 pi sampling of omega tau by 2. This becomes a delta omega. So you can have 2 pi into delta omega. So this is a constant time domain spectrum, and the corresponding frequency spectrum can be represented. So this is a constant, and corresponding frequency spectra is an impulse because 2 pi into delta omega it is. So if you want to calculate the Fourier transform of your right-sided sequence, f of omega equal to integral minus infinity to infinity f of t power j omega t dt equal to integral 0 to infinity e power minus alpha t e power j omega t dt. So this can be written as integral 0 to infinity e power minus alpha plus j omega t dt. So you can have 1 by j omega plus alpha. So if you write the magnitude and phase spectra of it, you can get like this. So this is the magnitude spectrum, and this could be the phase spectrum for one-sided signal. So once you calculate this try to calculate the Fourier transform of a sigma function. So sigma function is being defined at t greater than 0, you will get 1, and t less than 0, it is minus 1. So you have a positive pulse and negative pulse like this. And you can have a practical sigma function can be represented like this. So you write the exponential signal in terms of exponential signum of t equal to limit a tends to 0 e power a t u of t minus e power minus a t u of t minus e power a t u of minus t. So if I apply the formula based on the definition, I can have limit a tends to 0 to infinity e power minus a t e power minus j omega t dt. minus integral minus infinity to 0 e power a t e power minus j omega t dt. So if I simplify by integrating, and you will get 2 by j omega is the Fourier transform of a signal function. And corresponding Fourier spectra could be looked like this. This is the signal function in terms of time. This will be what is called spectra of signal function. Coming to the unit step signal will have a relation with signum of t equal to 2 ut minus 1, u of t equal to 1 plus signum of t by 2. So if I apply the formula of Fourier transform of a constant and Fourier transform of signal function, I can have 2 pi a delta omega into 1 by 2 plus 1 by 2 into 2 by j omega can give you pi into delta omega plus 1 by j omega I can. So this is the simple frequency spectrum of the signal. If this is the u of t, this will be the frequency spectrum of u of t. So now once you solve basic problems on Fourier transform, let us try to talk about properties of the Fourier transform. So before going to do it, you can have a notation of some notations. Fourier transform of f of t equal to f of j omega, and Fourier inverse of f of j omega equal to f of t. So this is both two forming a Fourier transform P. Fourier transform of t equal to f of j omega and inverse Fourier transform of this equal to f of t. So in the future slides, we are going to use this notation. So this is the linearity property. So this is the self-explanatory. I don't want to go into depth about it. Time scaling property. Fourier transform of at equal to 1 by a into Fourier transform of j omega by a. So this is the definition or maybe statement of the problem. So you can calculate the based on the definition of the Fourier transform. So f of Fourier transform of f of at equal to integral minus infinity to infinity f of x into e power minus j omega by x into 1 by a dx. Let here at is being represented as x. So I can have dx equal to a dt, dt equal to x by a. So I can have Fourier transform of at equal to 1 by a integral minus infinity to infinity f of x e power minus j omega by a x dx. So this is the what is called f of omega by a. I can have 1 by a into f of omega by a. So similarly, if time reversal is also similar to that, the time scaling a equal to minus 1, f of omega equal to this, and Fourier transform f of minus t equal to integral minus infinity to infinity f of minus t power j omega t dt. So this can be written as t equal to minus infinity to infinity f of minus t power minus j omega t dt. So if I write minus t equal to minus infinity minus t equal to plus infinity, so this can be written as f of t power j omega t into d minus t. So this can be written as minus t equal to minus infinity infinity f of t power minus j omega t dt. So this can be written as t equal to 0 to infinity, t equal to minus infinity to minus plus infinity to minus infinity. Here I have minus. This minus can be eliminated by interchanging the limits. T equal to minus infinity infinity f of t power j omega t dt. This can be written as simply what is called f of minus omega. Similarly, time shifting property. Fourier transform of f of t minus t naught gives you f of omega into e power j omega t naught. Let t minus t naught equal to I can consider as t and t equal to p plus t naught. So if I apply the formula based on the definition, I can have t tends to minus infinity infinity f of t minus t naught e power j omega t dt. So here I can write wherever t is there, I can have p plus t naught equal to minus infinity to infinity f of p power minus j omega p plus t naught dp plus t naught. So if I take e power j omega t naught as a common factor, p equal to minus infinity to infinity f of p power minus j omega p dp. So can give you e power minus j omega t naught integral minus infinity to infinity f of p power j omega minus j omega p dp. So this can be written as e power j omega t naught into f of j omega. Similarly, frequency shifting or modulation property can be calculated. F of t into e power j omega t gives you Fourier transform of f of j omega minus. There is a shift in the frequency. If I multiply the signal with e power j omega naught t, then integral minus infinity to infinity f of t power j omega naught into e power minus j omega dt. This can be integral minus infinity to infinity f of t power minus j omega minus omega naught t dt. This will give you f of minus j omega minus omega naught I can. So symmetry property is another one. Fourier transform of capital F of j t equal to 2 pi into small f of minus omega. So this can be proved by using the Fourier integral. So 2 pi into f of t equal to integral minus infinity into f of j omega e power j omega t d omega. So replace t with minus t. You can have 2 pi f into f, 2 pi f of minus t equal to integral minus infinity f of j omega t power minus j omega t d omega. So interchanging the omega and t, I can have 2 pi small f of minus omega equal to minus infinity f of jt into e power minus j omega t dt I can get. So this is the symmetry property of the Fourier transform. I can also calculate if f of t is a real function, the Fourier transform of f of omega equal to real part of omega into imaginary part of omega. F of minus omega minus j omega equal to f star of j omega can be written as f of t equal to integral minus infinity to f of t power minus j omega dt can be written as f of omega. This can be written cos omega t minus j sin omega t can be written as real part of omega and imaginary part of omega I can write. So this is a normal Fourier transform. This is the complex conjugate of the Fourier transform. So a complex conjugate of Fourier transform, if f of t is real, I can have f of minus j omega. So if the f of t is real function and the real part of f of omega is even and imaginary part of f of omega is odd. So that is fr of minus j omega equal to f of j omega, fi of minus j omega equal to minus f of j omega. So the magnitude spectrum of f of omega is always be even and the phase spectrum of f of omega is odd. So this is a consolidated way of representing f of t is real and even, f of omega is real. If f of t is real and odd, f of j omega is pure imaginary. So that is, this is the fundamental definition of even function. Similarly for odd function. So this is in terms of frequency. This is also in terms of frequency. So I can have, if the function is real, f of minus j omega equal to f star of omega and f of minus omega minus j omega equal to f star of omega. So f of j omega equal to f star of omega and f of omega equal to minus f star of omega. So this is what is called real and imaginary part of the function. So if you want to calculate the Fourier transform of f of t into cos omega naught. So we know that Fourier transform f of t equal to f of omega. Then what could be the Fourier transform of cos omega naught t? Cos omega naught t equal to 1 by 2 into Fourier transform of e power j omega naught t plus 1 by 2 into Fourier transform of e power minus j omega naught. So here we use what is called frequency shifting property of the Fourier transform. So Fourier transform of e power j omega naught equal to a constant into e power j omega naught t. So that can be 2 pi into delta omega. A is 1 here, 2 pi into delta omega minus omega naught plus 2 pi into delta omega plus omega. So here I have 1 by 2 is there. I can have pi delta omega minus omega naught and pi delta omega plus omega. So now you want to calculate Fourier transform of f of t into cos omega. So I can have 1 by 2 into f of t into e power j omega naught t plus e power minus j omega. So we have already calculated Fourier transform f of t equal to f of j omega and Fourier transform of cos omega naught t equal to pi delta omega minus omega naught plus pi delta omega plus omega. So this is the frequency spectrum of the cos omega naught t. So as two signals are multiplied, same signals are convolved each other. I can get the overall Fourier transform of f of t cos omega naught equal to 1 by 2 into f of j omega minus omega naught plus 1 by 2 into f of j omega plus omega. When f of t equal to 1, this becomes 2 pi delta omega. So this is what is called this. So this is the Fourier transform of a what is called your radio frequency pulse, varies from d by 2 to plus d by 2. So it is a combination of two functions. One is a rectangular pulse, another is a sinusoidal signal. So rectangular pulse is being defined like this, and we take the Fourier transform of it. You can have 2 by omega into sine omega d by 2. This we have already done it. And Fourier transform of a cos omega naught t equal to pi delta omega minus omega naught plus pi delta omega plus omega. So if I take a Fourier transform of it, when two signals are multiplying each other, same signals are convolved each other, I can get sampling of this convolved with this function give you sine d by 2 omega minus omega naught by omega minus omega naught plus sine d by 2 omega plus omega naught by omega plus omega naught. So another example of the same can be represented like this. And corresponding frequency spectra could be represented in this way at omega, minus omega and plus omega. So I can also use the symmetry property to find the Fourier transform of a sine AT by pi t. So if I want to calculate the Fourier transform of this signal, we know that Fourier transform of a rectangular pulse is equal to 2 by omega into sine omega d by 2. So use the symmetry property, omega replaced with t and t replaced with omega. I can have Fourier transform of 2 by t into omega replaced with 2 by t sine td by 2 equal to 2 pi into wd minus omega. So because it is symmetric each other, Fourier transform of t equal to sine at by pi t equal to omega 2a minus omega. So this is equal to 0 for omega is less than a and equal to 1 for omega is greater than a. So coming to the differentiation property, Fourier transform f of t equal to f of j omega, and then f dash of omega equal to j omega into f of j omega. So we know that f of t equal to 1 over 2 pi integral minus infinity f of omega e power j omega t d omega. So if I differentiate with respect to t, d by dt of f of t equal to 1 over 2 pi integral minus infinity f of j omega into d by dt of e power j omega t d omega. So if I differentiate it, you will get 1 by 2 pi integral minus infinity into j omega into f of j omega e power j omega t d omega. So whatever the formula I can have is a Fourier inverse of j omega into f of j omega. So if I take like this, I can have Fourier transform of d by dt of f of t equal to j omega into f of j omega, which is equal to Fourier transform of f dash of t. So I can also calculate the Fourier transform of a simple linear line, varies from -1 to +1. So x of t can be written as t equal to -1 to +1. I can use the differentiation property here by simply differentiating this. I can have a rectangular pulse followed by two impulses. One is at -1, one is at +1. You will have a rectangular pulse like this. So if you differentiate it, you will have this can be written as minus delta t minus t plus t plus 1. This will be minus delta t plus 1 followed by a rectangular pulse. So if I take a Fourier transform of it, y of t equal to e power minus j omega minus e power plus j omega plus integral 1 to -1 to 1 e power j omega t dt. So if I do it, I can have -2 cos omega t plus 2 into e power minus j omega minus e power plus j omega by total divided by -2j. So this can be written as sine omega. So -2 cos omega plus sine omega you will get. So according to differentiation property, y of omega equal to x of omega into j omega. You can have 2 cos omega plus sine omega by omega. So if I write, I can have x of omega equal to 2 sine omega by j omega square minus 2 cos omega by j omega. I can. Similarly, the integral property can be calculated. Fourier transform of f of t equal to f of omega. Fourier transform of integral minus infinity f of x dx equal to 1 by j omega into f of omega. So here I am assuming phi of t equal to integral minus infinity f of x dx and limit t tends to infinity phi of t to be 0. So Fourier transform of f dash phi dash of t equal to Fourier transform of t. So Fourier transform f of t equal to f of omega, and Fourier transform of phi dash of t equal to j omega into phi of j omega. So phi of j omega equal to 1 by j omega into f of j omega. I can take. So differentiation, derivative of the differentiation in frequency domain, if you want to do it, Fourier transform of minus jt into f of t gives you d by d omega of f of omega. So we know from the definition f of omega equal to integral minus infinity to f of t power minus j omega t dt. So if I differentiate it, I can have d by d omega integral minus infinity to f of t power j omega t give you what is called integral minus infinity f of t d by d omega of e power j omega t dt. So you can have integral minus infinity minus jt f of t into e power j omega t. So this is what is called Fourier transform of minus jt into f of t. So now the convolution property. So before going to talk about convolution property, first of all we have to define the convolution. So convolution of two signals can be written as f of t equal to integral minus infinity f1 of tau f2 of t minus tau d tau. This is what is called f1 of t convolved with f2 of t. So here I have a property what is called a commutative property. f1 of t convolved with f2 of t equal to f2 of t convolved with f1 of t. So we are not going to talk about this property right now. We will discuss it later. Now our aim is to calculate the Fourier transform of the convolution of two signals. When f1 of t convolved with f2 of t, you can have f1 of omega with f2 of omega. Because when two signals are convolved in time domain, same signals are multiplied in frequency domain. So that is Fourier transform f1 of t convolved with f2 of t equal to integral minus infinity integral minus infinity f1 of tau into f2 of t minus tau d tau e power minus j omega t dt. This can be f1 of tau, you can take common, and integral minus infinity f2 of t minus tau e power j omega t dt d tau. And we know that this is equivalent to f2 of j omega t e power minus j omega tau. So if you write like that, so I can write f2 of j omega, I can take as a common factor. So integral minus infinity f1 of tau d power minus j omega t d tau can be written as f1 of omega. So this can be written as f1 of omega into f2 of omega. I can. So here the time domain in convolution gives you frequency multiplication in frequency domain. So that is one. So when two signals are convolved, we said that same signals are multiplied in frequency domain. Suppose if two signals are multiplied each other, then in frequency domain the same signals are convolved. So that is f1 of t multiplied with f2 of t gives you 1 over 2 pi integral minus infinity f1 of j theta f2 of j omega minus theta d theta I can get. So to prove this property, what I am trying to do is I take Fourier transform of f1 of t multiplied with f2 of t gives you integral minus infinity f1 of t f2 of t power j omega t dt. That is integral minus infinity 1 over 2 pi integral minus infinity. So I can write f1 of t as 1 over 2 pi integral minus infinity f1 of j theta e power j theta t d theta into f2 of t e power minus j omega t dt. From here I can take 1 by 2 pi integral minus infinity of 1 of j theta as a common factor, and I can write integral minus infinity e power j theta t e power minus j omega t f2 of t dt d theta. So this part I can write as f2 of j omega minus theta. Of course theta would be there. I can write 1 over 2 pi integral minus infinity of 1 of j theta f2 of omega minus theta d theta gives you convolution of two signals in frequency domain. So that is frequency domain. So when two signals are convolved in time domain, same signals are multiplied in frequency domain. When two signals are multiplied in time domain, same signals are convolved in frequency domain. Suppose if omega equal to 0, then I can have integral minus infinity f1 of t, f2 of t dt equal to 1 over 2 pi integral minus infinity infinity f1 of j omega into f2 of minus j omega d omega. This is a simple Parseval's theorem. So when integral minus infinity into f1 of t, f2 of dt equal to 1 over 2 pi integral minus infinity infinity f1 of omega into f2 of minus j omega d omega. When f1 of t and f2 of 2 are real in nature, then it becomes 1 over 2 pi integral minus infinity into f1 of j omega into f2 star of j omega d omega. So this is the Parseval's relation between one signal with other signal. Right? So now the Parseval's relation or Parseval's identity, you can write integral minus infinity infinity modulus of f of t square dt equal to 1 over 2 pi integral minus infinity infinity can be written as modulus of f of omega square d omega. So this is the Parseval's identity. So you know that Fourier transform of f star of t equal to integral minus infinity infinity f star of t d power minus j omega t can be written as integral minus infinity infinity f of t power j omega t dt whole star. So this is f star of minus omega. So when you write the equation integral minus infinity into f t square dt can be written as integral minus infinity into f of t into f star of t dt. Now I can write 1 over 2 pi integral minus infinity infinity. So f of omega into f star of minus omega. I can get integral 1 over 2 pi integral minus infinity infinity modulus of f of j omega square d omega I can get. So this is what is called your Fourier transform and its properties. If you have any doubts, you can ask me. I am trying to